Very welcome. Good morning. So every time that I give this lecture, this lecture is only the second time, but every time I give a machine learning lecture, I ask myself, what is still relevant and what is still meaningful to learn, because the field develops at breakneck speed. The rate of an interesting question is what's the rate of fundamental ideas versus what's the rate of just technological progress. But there's an interplay, a close interplay between the two. And so this year I asked myself very seriously, in the year 2024, is it still appropriate to talk about convolutional neural networks? And I'm not the only one asking himself or herself that question. You see, I made a decision. And this was also at the heart of a heated debate earlier this year, so-called Twitter feud, or as you now have to say, an X feud, because between some LeCun, inventors of convolutional networks, and some Elon Musk, richest man in the world currently. And the argument started about the billionaire advertising for people to join one of his companies, and then LeCun making some funny remark about, yeah, if you want to, deliver solutions to unsolvable problems next year and work day and night and so on, that's a good idea. Go there, do that. And then the billionaire took offense and said, what have you been doing anyways? And LeCun said, well, I invented CNNs, amongst other things, so convolutional networks, or CNNs for short. And then Musk answered, well, CNNs, we don't use them much these days, to be honest. And then LeCun more or less proved to him that every autonomous driving system does use them, including Tesla. And then Musk went quiet, either because he had to, attend to more urgent matters, and or because he knew or was informed by his staff that yes, he was wrong. Yeah, so CNNs are still being used in, for example, fully autonomous driving systems where you need to make many, hopefully accurate decisions, at a very high rate, like 30 frames or so per second. So yes, I think it's still worthwhile talking about them today, even though I have to say they rule supreme. Their reign was from 2012 to 2020 or so. So 2012 was when AlexNet blasted on the stage, and 2020 was when transformers made it into vision in the guise of vision transformers. And this is not the very last word on the matter. There have been papers later, like in 2022, there has been a paper called ConvNext, which says that, okay, if you build truly modern architectures using CNN motifs, and if you give them as many parameters as you would normally give transformers, then you can even be better. And okay, and then it took a while, and currently transformers are leading by a small margin again in vision problems. All right, so they're practically useful, and they are the first example I want to discuss in this lecture of a so-called inductive bias. This was a very fashionable term a few years ago. If you were a self-respecting machine learner, you had to, put inductive bias into your paper at least once and into your conversations also. And one way of looking at the remainder of this term is to say that, yes, we will look at different inductive biases. Yeah? And the first and simplest one, arguably, and the one that's incorporated in convolutional neural networks is shift equivariance or shift invariance. Why so? Because as the name implies, these systems are convolutional, but let me start with a non-convolutional system, okay? So let's say we have a one-dimensional signal, because for me this is easier to draw than images, okay? So we have here our 1D input. And if we now operate on this 1D input with a multi-layer perceptron, we have been writing something like sigma W transpose X. So X was our input. W has been the weight matrix holding all the weights for all the perceptrons. And then we put the whole thing through a nonlinearity. And this 1D input could be, let's say, a bit of a speech signal, or it could be one line from an image. But speech is a good example, okay? If we just if we say this is time, and if we just plot the amplitude of what I say over time, for example, when I do dictation on my phone, and when I want my dictation to be translated into letters, this would be the input. All right. So, just to make it more redundant, the alternative representation would be to say that, yeah, this is the input, and now I have many, many, many perceptrons, not drawn to scale here. And the first perceptron takes input from the full signal, and the next perceptron takes input from the full signal, and so on. Yeah? And then each one has its own nonlinearity, and that would be sigma W transpose X. If we omit the nonlinearity, we focus on this part, and here I show that as a matrix vector multiplication. All right, this is W, this is X, and this is the product between the two. And now in a general MLP, this matrix would be dense. So I would have no particular sparsity pattern here, and if my input is p-dimensional, this is p times 1, then the number of parameters that I have here, number of parameters in this case would be p squared. And if I want to add biases, I need to add another p. All right. Now, if my input signal is long, so let's say I have a speech signal, take 10 seconds, sample it at 1,000 hertz, which is not very much, then we would have 10,000 here, and this would be a 10,000 by 10,000 matrix, so that's 10 to the 8, and that can get large. And for images, it's even worse. For images, our input, I easily have 1,000,000 pixels in the image, and then this would be 1,000,000 by 1,000,000 matrix. So MLP has rather too many parameters if you want to operate on contiguous signals like that. Now, the next thing I can do is to say I want a locally connected neural network, or MLP. So in this kind of picture here, what I would say is that this is my input. These are my perceptrons. And now each perceptron, I'm taking one in the middle here, is not connected to all parts of the input, but only to maybe 3 samples. And in this moment, my matrix here, well, it becomes banded, right? So I have if I have 3 inputs, I need 3 multipliers for these 3 inputs, and the rest is 0. And the number of parameters in this case would be, if my input here is p-dimensional, number of parameters would be p, and or 3p. So let's say p times const. And that's it. All right, so how can I push this even further? Well, I can force this matrix not just to be banded, but I can force the weights to be constant. So I can say, all right, I'm taking a parameter W1 here, and I'm repeating this along my full diagonal. And then I have a parameter W2, and I'm repeating that along the diagonal, and I have a parameter W3, and I repeat that. And the number of parameters in this case, okay, if I omit the bias, the number of parameters here would be 3. Yeah, so we have 10 to the many, and here we have 3 or 5 or 7, but some tiny number. The picture I would draw here would be the same, except that now all of these perceptrons are identical copies of each other. Okay, and this would be an example of a convolutional neural network. And well, convolutional it is because if I make this matrix here, I can even make this a circulant, or if I want, that would introduce periodic boundary conditions. This would be the same thing as convolution. Yeah? So if I write it in the continuous domain, if I call my input f, and if I call my kernel, let's say x, my filter kernel, and then if I, depending if it's discrete or continuous, if I integrate or sum, so here I sum over x, I obtain some function g of z, which would be my output. So this is the very definition of convolution. And if I have not a continuous signal, but a discrete signal, this becomes a summation, and repeating the filter over and over gives me this kind of triplets matrix here. All right, and this in signal processing would not be called, or in signal processing, this kind of system is called LSI, which is shorthand for linear shift invariant. Well, as long as we don't have this nonlinearity, yeah? So we're just talking about this part of the operation here. You can see, I think, that it's linear, and shift invariant means if I have this kind of matrix, triplets matrix, if I now start to circularly permute my input, so I just shift my input a little bit, and the samples that go out at the end, I put them back at the top, then the result will also just shift. Yeah, or if I, another way to express this is if I put a shift operator here that's acting on my input, then I will obtain the same output, just, well, dislocated or shifted by the same amount. Okay, so this is why the structure is called convolutional, and it was really developed in the context of images. So for images, this means, and I'm now moving to this kind of representation here, we have some input image, and then we convolve this input image with a tiny filter, and then there have been heated debates. I'm sorry, I'll redraw this filter. There have been heated debates about how large it should be. And a popular choice for a long time has been to use 3x3 filters. So here I was talking about we have 3 distinct weights. In this 3x3 filter, I have 9 distinct weights. And well, this the result of this convolution is another image. And this image I can now put through a pixel-wise nonlinearity. For example, rectifying a linear unit or so. And this would then be called one channel. And if I take the same input image and I convolve it with the second filter, then I get a second channel. Yeah? And what typically happens in these NNs for computer vision is that we have a couple of channels which all together correspond to one layer. So I should, okay, let's say I convolve it with this filter, and okay, now I go multimedia here, or at least multicolor. So let's say I'm using 3 different filters here. And then the result will be these 3 different channels. So that's a very typical operation. So even if I input a gray value image, so sometimes I just have a cheap camera, let's say, or I have maybe, you know, a different monochrome source. Anyway, I have a gray image. I use a couple of filters, and maybe not just 3, but maybe 64. Then I get 64 channels. And at the next stage, I can now again use a convolution filter. So I put this through a nonlinearity. And so this couple of channels, because it's too much work to always draw them separately each time, I can also draw them as a small box like so. Okay, so this would be my channels. So the dimensions here, for example, are maybe 512 times 512, if that has been the dimensionality of my input image, times, all right, in this particular case, let's say it would just be 3 channels. And now I can again convolve this with a small convolution mask. Let's say I again use 3x3, and this convolution now happens. So this convolution mask here would be 3 by 3 by 3. The first 2 are the spatial dimensions. The last number here gives me, that should be the same as the number of channels that I have here. And this convolution now happens only in the spatial domain. Yeah? So I move my mask around, I always compute this inner product, and as a result, I get one single new channel. Yeah? If I just use one single of these filter masks here. And all right, sorry, this was 3 channels, so to be exact, it would look like so. Good. And then I can again use multiple of these weight masks. I get multiple of these channels, which I can combine into a layer and so on. Yeah, so that would be a typical building block of a convolutional neural network. And the way I have shown it so far, the number of entries always stays the same, but that's not necessarily the case. We can also have upsampling or downsampling operations. So upsampling can be used for super resolution if I want to create an image of higher resolution than I had originally. Downsampling is useful to obtain reduced descriptions of the image. And now I return to that kind of picture here. So previously, we used an input that was p-dimensional and a p by p mask, and the result of this was again p-dimensional. But I can also choose, so I'm always fixed in, so this, the second dimension here is fixed, but the first one I'm free to vary. Yeah? So for example, I could decide to make the first dimension here twice as long of my weight matrix. So for example, this would be 2p by p, and then the result, of course, will be 2p by 1. And I can still make this convolutional, so I can still have weights, but now my diagonal becomes slanted. Yeah? And so I can start interpolating. This here would be interpolation. Or I can downsample. I use the corresponding trick, so I have a p-dimensional input. But for this kind of mask, my output would just be, so if the input here was p times 1, the output here would be p half times 1, for example. And these things are also called, in the literature, these are also called transpose convolution. So this is one way of downsampling, and another way which is frequently used is the so-called max pooling operation. As the name implies, in max pool, I look at a couple of inputs. For example, I look at 2 by 2 pixels. So now I'm switching images again, pictures again. Now I'm looking here at the 2 input dimensions. And then a max pool operation would just take, it would just pass on to the next layer the maximum value out of these 4 activations. So this will reduce in the next layer, this will reduce the spatial extent by a factor of 2 in both dimensions. And in backpropagation, by the way, this in the forward pass, we then need to remember which was the maximum pixel. And in the backward pass, we then route the gradient to that pixel that was the largest amongst its neighbors in the forward pass. Okay, so shift invariance, I was saying approximate shift equivariance. That's because in situations like this, so coming back to this inductive bias, yeah? Why is it useful to have the shift equivariance? Because if I take, you know, this photograph and then I move my camera by 2 millimeters and I take the same picture again, and if I show it to a human being and ask, you know, is there a meaningful difference between the pictures? The answer will be no. And then if I tell the human, well, but there is a difference, can you spot it? Then the human will probably not be able to do it. But if I give the digital image to the human, who is a scientist, and ask her what's the difference between the images, then she can take the difference between the 2 images and see that, okay, there has been a tiny shift between the 2 images. So there has been a tiny shift. There is a true difference between the images, but this kind of difference doesn't matter to us humans, yeah? Or in the interpretation that we have for an image. And this is why we want our result. For example, if we want a textual description, you know, create a text describing what's happening in the image, this text should not depend on if we have shifted the image by 1 pixel or not. Or if I have, you know, let's say a face detection system running, then my face detections, they should change by 1 pixel or shifted by 1 pixel, but they should not change. So the number of detected faces should not change, for example. Okay, so this is why in images this kind of shift equivariance is interesting to have. And now in systems like that, this equivariance is only approximate, because we always push this through a nonlinearity subsequently. And here my pixel masks, they are displaced by more than 1 pixel. So for example, if I have a okay, or we can, maybe it's easier if I argue in terms of the max pool operation. So the first image created a couple of activations, and one of these 4 was the biggest. Now, if we run this max pool on if we run this max pool on 2x2 patches which are adjacent to each other, then if I shift my input by 2 pixels, so by a multiple of this max pooling window size, then the output will be shifted, but it will not change otherwise. But if I shift the input by just 1 pixel, then the output can truly change. And this is why I wrote here that this kind of system is approximately shift equivariant, because even in a CNN, we do use transpose convolutions or we do use max pooling operations. So they're not truly convolutional systems. Okay, so approximate shift equivariance is a useful inductive bias to have. And later in the lecture, we will look at other biases like permutation equivariance or equivariance with respect to rotations in 3D space. And this gives rise to interesting architectures and mathematical problems. All right. Now, this lecture, what comes next will use many pictures, and that means I will go away from the blackboard for the remainder of today. Before I bring down the screen, do you have any questions about this? Yeah. So the way I understood the question is, how do I choose these weights in the interpolation case? Yeah. So let me try and draw a different picture for this interpolation case. So we have let's say we have now in this 1D example, we have our input here. And now I have, without the interpolation, I have this kind of perceptron, and it uses these weights W1, W2, W3. Yeah? And now I'm drawing the same perceptron. Okay, so here we have this weight sharing. Yeah? The first weight is all the same, the second weight is all the same, the third weight is all the same. And now I have a second kind of perceptrons, the interstitial ones. And these interstitial perceptrons, they still use, and now I need to, break symmetry and say, for example, they always operate here to the left-hand side. And now the drawing is getting a bit messy, sorry. So I had the white perceptrons, and then I had these red perceptrons. And the weights for these red perceptrons so they're amongst all the red perceptrons, they are the same, but they can be different from the white ones. Yeah? Yeah, they accept the same input. Yeah, so like in this picture here, they operate on the same input. It's just a bigger matrix. Okay, and there was another question somewhere. The question was, why are CNNs not used as much anymore? Because, so I would like to give two reasons. One is there are a number of benchmarks, and we can, so for example, these benchmarks, they were really important in this era. So a famous benchmark was ImageNet, which is not the proper name, that's the colloquial name. This was the benchmark where the computer had to distinguish not just is it a cat or a dog, but which type of dog is it. And on this type of benchmark, you can just say which architecture has the highest accuracy. And there has been a jump in performance in 2012 when AlexNet came, and then things got better over time. And the last winning architectures happen to be transformers. But the last winning architectures, they date from 2022, which is a long time in machine learning. So basically, people have abandoned those benchmarks because they're no longer interesting. And no longer interesting, why? Because they're, let's say, solved. And the main focus these days is on foundation models that have hundreds of billions of parameters. And to train these, you cannot train models with so many parameters on such relatively small benchmarks anymore. Basically, you can only train them on the internet as a whole. And the internet as a whole, well, it has lots of images and lots of text. And if you're lucky, the text somehow refers to the images. Yeah, so on most web pages, there's a picture and there's text, and hopefully there is some relation between the two. And so nowadays, you try and train models that use text and images jointly. And we will see how that is done using CLIP architectures and such. And in this case, you need an embedding of a constant dimensionality for an arbitrary image. And you also want text of arbitrary length and map it to a constant dimensionality. And in fact, text and images in these architectures are mapped to the same space. And on text, you cannot very meaningfully operate with CNNs. There have been attempts, but really transformers shine when you deal with text. And transformers can also be very successfully applied to images. And then transformer architectures are used on both text and images to map them to the same space. So this is why pure CNNs, they're still super useful in specific applications like the automated driving, or if you have very specialized segmentation problems or so. But by and large, we now see the rise of the foundation models that have been trained on the internet, and then you fine-tune them on your task of interest. So the field has simply moved on. And this has been, the 2012 to 20 has been an amazing time because, previously computer vision, it really didn't work. Yeah? So what we could do by 2012 as a community, we could reliably detect faces. We could, if we were pushing it, even recognize faces. But it was basically computer vision worked successfully in niches, and you had to retrain you had to reinvent a pipeline or retrain your pipeline for every specific problem. And then in this short period, in the type of benchmarks I mentioned, computer vision reached human accuracy and then surpassed human accuracy. So that was, extremely fast development. And it has not surpassed human computer vision, or it has not surpassed human vision in all respects. So for example, I've been talking about automated driving a lot. Where the systems still struggle a lot are difficult pictures. So mainly by that, I mean, if it's night and raining and lights are glaring and, perhaps there's a bit of, snowfall. So difficult lighting conditions is where these systems still really, really struggle. And this is one of the prime reasons holding back this fully automated driving systems. The other one is that they are still not so good at dealing with rare situations. So humans have this pretty solid world model. And even if there's something that we've never seen in the training data, most of the time, at least given enough reaction time, we're able to figure it out. And these systems still struggle a little bit with generalizing to extreme or to very rare scenarios. So they are still being used, and the fact that they are is what motivates me to talk about them today. Yeah? Any other questions? Okay, so we still have, I think, a bit of time before the break. And okay, I'll just say something short. So now I will show many pictures, and I will not write anything, so it's up to you to take notes, and it's up to you to figure out when I'm rambling and giving my opinion and when I'm telling scientific fact. Yeah? And the lecture mainly today is about convolutional networks. And besides, it also is about resilience and going against the mainstream opinion in science. And I have two examples, one before the break and one after. So the first example is LeCun himself, because LeCun has been out in the wild for a number of years before 2012. So he became a name in science in the late 90s when he was publishing architectures that were called LeNet. And these LeNet, weird, tiny CNNs, they were the first that could reliably read digits. And he was working with AT&T labs at the time, so in telecommunications, and this LeNet was eventually really used to sort letters. Yeah? So in mail distribution centers, just to read the postal codes and to see where to send a letter. So this was a success. This was the late 90s. And then I saw him give a talk sometime in the early 2000s. And he was showing, and this was before GPUs. So he was building this tiny robot that could somehow, navigate a little bit and do a little bit of real-time processing. And this was something that nobody else could accomplish at the time. And there was a lot of engineering involved. Because there were no GPUs, the neural networks had to be tiny. They had the architecture very, very tailored to what could be made to run in real time. And the community said, yeah, that's an impressive engineering feat. Nice that you can do that. And then they went on and did their lofty science instead, because nobody liked, this engineered stuff. And he somehow stuck with it as one of a really small number of people. And then in the beginning of the semester, I said, bam, came AlexNet, yeah? Because really AlexNet was a qualitative jump in these benchmarks where accuracy had sort of stagnated beforehand. So I think what was the case for LeCun was that people didn't like the engineering, and people were, and that includes me, I was much in love with stuff that I can understand and where I can do the math properly and so on. And all right, eventually the neural networks won. And now in hindsight, everybody is finding, interesting mathematical aspects to these and, sort of cleaning up the mess. But sometimes it's, it just takes this courage, to, go ahead and do something, maybe not quick, but dirty, that works, and then figure it out afterwards. I think that's a lot of time what the mathematicians say to the physicists, that the theoretical physics, it does something weird in math, and then 10, 20 years later, the mathematicians clean up the mess, and then it becomes sort of accepted, yeah? And then it's okay after it has been cleaned up, but before it was not. And to some extent, the same happens occasionally between engineering and physics. So, engineers do something and physicists say, nah, that can't work, or if it does, it's not interesting. And then in the end, it does work. And then the mess needs to be cleaned up and it needs to be understood, okay, this semiconductor, why does it semiconduct? Or this supraconductor, why is it superconducting? And so on. Yeah? So people who first build the stuff, and then after the fact, we find out, or try and find out why. Yeah? And yeah, so there's a lot to be gained from this mutual respect between the disciplines. And I sometimes need to remind myself to also respect the people who just build some stuff that works, even if nobody understands it at the time. Yeah? And sometimes that can give really interesting input to this, yeah, can give real scientific stimulus. So LeCun was out in the wild between the mid-late 90s and 2012. And okay, in the end he prevailed, but he really had to go through, I would say, a very difficult professional period. And he stuck with his ideas. Okay, and the second example I will give you after the break. Let's have a 10-minute break.